It is a predictable event. Okay, so correlations. Hopefully today will be like kind of a brain break. We do only have 3 weeks left. I don't know if you guys thought about that yet.
No.
We do have the entire week off for Thanksgiving, which is new for MSU. And then when we come back, we'll be doing factor analysis. So we're going to start with correlation, go into regression, hopefully do some mediation and moderation next week, and then end with EFA. And so I know you all know what correlation is, but just to go over it. So it's a way of measuring how much two things are related. And so it's going to measure the pattern of responses across variables. So the whole last section, what we've been dealing with is categorical IVs and continuous DVs. This section is a mix of both. Generally, correlations are on two continuous variables, but not always. So we'll look at what happens if you have a categorical variable and a continuous one. And we don't really have IVs and DVs anymore because correlation, the directionality doesn't matter because we can't predict direction. So if I'm looking at a scatter plot, this would be no relationship between variables. So it will look like just a big bunch of dots, which is what we're used to looking at for homogeneity charts or homoscedasticity charts. But there's no relationship between X and Y in this chart. Maybe slightly positive, but mostly nothing. If I was to get a positive relationship, right, as one variable goes up, the other variable goes up. As X is going up here, Y is also going up, so it will lean to the right. Left and right are hard. So that is a positive relationship between variables. And then negative relationship between variables is as one variable goes up, the other one goes down. Okay. This should not be new to any of you. Right. But what we're going to get into today is how do I test the differences between correlations? That's generally a question I get asked at least twice a year that not a lot of people know how to do. What about partial correlations? Non-parametric correlations. So we're going to take correlation and extend it. So not just talking about what is R, but also what is other alternatives to R. So a quick reminder, since we have not made scatter plots in a while, in ggplot. So we'll do its data. So you do X comma Y still. So whichever one you want on the bottom, put it first. But now they're both going to be continuous. Your color or your fill variable will be categorical. So this is if you want to split by gender and look at guys' correlations and girls' correlations, then you would use color and or fill. Okay, more than likely it's going to be color, right? Because color will give you the color of the dots will be different. Fill is if you're adding the regression line, and that'll change the fill of the confidence interval band. Okay. Plus all of our theme coding that we've been using all year. Geom point, that gives you the dots. Geom smooth gives you the line, and then X and Y labels. So what we can do to start is we're going to work with that exam data we did for chapter 4, and then also some other data that I have. So you'll want to load up the exam data. And my gender variable is not factored in this. So I'm going to go ahead and factor it. And then it imported Goofy, but I'm not going to use that variable, so I'm going to leave it alone. So we've got our gender variables. It's factored, and our exam data is loaded. And just as a quick aside, I was telling my better half, he was like, how's your semester going? I was like, that's such a loaded question. Why? Which class? Yeah, which class, which problem? But we were talking about, like, everybody's like, oh my God, R, help. And so it's funny to me to listen to you guys talk now about it, because you're like, oh, I forgot to see that. Whereas the first week it was like, oh my God, what is she talking about with this C thing? So you're much better at it than you realize. As we go back earlier in the semester, Scatterplots, just remember if you're not sure what's going on, you can use this code or go back to chapter 4. So let me load up ggplot on my computer. Once you guys get everything loaded. Heaven forbid the internet be out really one day. Would like just be drawing on the board. You'd have to go like old school transparencies. All right, there we go. So I still got my theme coding that I've been using.
We should do that one day. Just show them that they need to fix the internet.
Well, it was out one day, but it like came back on right before class. I was like, phew. So a simple scatter plot for this exam data, which has how much anxiety there is before the exam score, and how much time you spent revising it. We've got exam data here, my aesthetic, just X and Y. So this is a very simple plot. Whoa, it's huge now. And so I'm just going to add points to it and an X and a Y score. And so we could look at this scatter plot and talk about it being a negative relationship. So as my anxiety score goes up, my exam score goes down because I'm too anxious. But it's also slightly curvilinear, especially because of these points out here. So I would say it's actually not totally linear, but we could put a line on it if we wanted. If I wanted to add that regression line, it's this geom smooth thing. Remember we used method equals LM to get a straight line, so we're not going to do any curvilinear stuff in this class. If you take that out, you will get a curved line. But I can add the line to the graph. And so we'll add that confidence interval band. So if you want the dots to be a different color, that's color. If you want this confidence band to be different colors, that's fill. Okay, so this is one of those awkward times where you have to use both scale color and scale fill. If I want to do a grouped scatter plot, so you've got color up here, I've got fill down here. But what I could do, bless you, I think, is put both of them up here. Let me test that. Yeah. So you can put color and fill in that first aesthetic line, or you can leave it with the line itself. So the fill part, it doesn't really matter where you stick it, but if you don't have it in there and ask for a regression line with a group scatter plot, it will give you, it'll freak out. So I can also create these different scatter plots. And this is one that we spent a lot of time figuring out how to color it and how to fill it. So this is like a cleaned up version. And separate them out by gender. So something new that we've kind of been talking about but haven't totally figured out how to do, because sometimes it freaks out. So not only now do I have to be concerned with the proper labels on X and Y in my legend, I have to make sure X and Y are appropriate length. And we tried to do a little bit of that, and sometimes the bars just disappear, and you're all going like, why? And I'm like, I have found the solution. That rule is less strictly enforced than on bar graphs, but I do want y'all to pay attention to it. There are several ways to do it, but this way is the one that doesn't give you the error. So chord Cartesian is a function that just kind of zooms in. The other function that we've been using, doing X and Y limits, actually cuts off the data. So it actually will calculate the graph based on only that range of data, which can mess up a regression line, because you usually want the regression line on the entire data set. So chord Cartesian just kind of smushes the graph, or expands it, depending on what you're interested in. Okay. So it will not give you the points excluded error, and it won't make your bars or your dots disappear. So it's XLim for X limits, YLim for Y limits, and you have to have two numbers. So give it an upper and a lower. If you give it one number, it kind of goes, I don't know what to do. And you can do one or the other. You don't have to do both, but I just showed you how you would do both. So I took my simple scatter plot and I cut off part of the limits. So what I did for Y, which is exams, is I just said, show me everyone who's passing. Now I did 101. Even though the limit of Y is 100, people can only get 100 on the exam, 101 gives me just a little bit of space so the dots aren't cut off. And I was just playing around with it. So let me show you that. So what I've done is cut off the bottom. So here, now the lower limit is 60, so this is the correlation for only people who passed. This would not cut off, actually exclude those people in any calculation. It would just zoom in the graph to this area. Does that make sense to people? Yeah. And the 101 allows me to keep the 2 dots up here on the screen. Otherwise, it kind of cuts them off. So it's a simple way to control the x and the y limit that can be applied to bar graphs as well. I just haven't figured out which way worked best, and this one seems to work with the least number of errors. So something new. Now back to theory stuff. So we started the semester with each person's score, some sort of outcome, was equal to some sort of model plus error. And we always want to start by looking at the scatter plots, mainly because then you can tell if you expect it to be positive or negative, or is it curvilinear. Right? So that's a particular issue if it's curvilinear, because then you shouldn't be doing these types of correlations anyway. So always look at a scatter plot first. But then when you get into calculating numbers for this, we have this model of, this setup where we're getting somebody's score as a model plus error. And with ANOVA and t-tests, right, the model is your group variable plus standard error. So we're using our different groups, their means, as our model, which is what we graph, right? And then standard error in some form, or residual variance, error variance. But we can't really do that with 2 continuous variables, because we don't have groups, so we have to come up with some sort of new type of model. So I think, oh, my slides got out of order. That slide should be here. This slide should be there. Whatever. We're going to switch to now for correlation and regression. Not EFA, it's going to be its own separate thing, is using either R, B, or beta. When you have one predictor, that's in like tiny type. It should be in like 75-point font. But this little line down here, show you highlight it. When you only have one predictor, one X, one Y, B, beta, and R are all the same thing. So for correlation, R, B, and beta, this is all the exact same thing. When we get into regression, we'll talk about when they're different. And that is actually what this slide kind of covers. So previously, we were using group means and standard error. And we use standard error to talk about fit. This is a million years ago now, right? We'd say which group has the best fit, that was example 1. And you were looking at standard error, which one has the largest standard error and the smallest standard error. Now what we're going to do is talk about R for this chapter. Yes. So we're going to do BX plus error. So one of these implicitly has to be X and one of them has to be Y, although we could switch them right now and it wouldn't matter. So it's going to be B as in the regression slope, R, which we traditionally think about as correlation coefficient, or beta, which is the standardized regression slope to determine model strength. Error is implied. And you'll see why here in a minute. But if we're using R, there's not a standard error for R reported normally, because R includes the error. Sometimes you'll see confidence intervals. Confidence intervals are correlations. There's no nice way to talk about them. They suck. So it's really nice because one of the functions we're going to use just pops the confidence interval out for you. It's beautiful. It's wonderful. I texted Rachel. I said, go back and look at your notes for this chapter and tell me how much you hated it. And she was like, oh God, no. I was like, guess what? We don't have to do any of that. She was like, yay. So sometimes you'll see confidence interval. Often you don't because it is so difficult to calculate. And SPSS does not do it for you, so a lot of people are just like, I'm gonna leave it out because I don't want to do all this math. But I'm going to show you how to get it, which is good. So what we're going to do is talk about R specifically today. But remember that when we get into regression next week, all three of those are the same value if you have one X, one Y. So what do I mean when I say that R has error in it already, and I don't need an extra error number? So what we're actually going to calculate is covariance. So if I have two variables with a positive relationship, what we're going to do is calculate how much do they vary together. So as this variable goes up, does this variable also go up? Or as it goes up, does the other one go down? Or does nothing stay the same? And so that's called covariance. You've used covariance throughout the year when we've talked about Mahalanobis distance. That's what the COV function does. So you've actually done covariance already, you just don't realize it. Okay. So the way covariance is calculated is we're looking at how much each score deviates from its own mean. And if the variables are deviating in the same direction, they're going to be related. Okay. So let me try and draw this for you. Let me do a better graph here. Let's say I've got anxiety and exams, okay. And that's a negative relationship. Okay. If the exam score average is this, and the anxiety average is this. Okay, everybody still with me? So I got the average of each variable. I tried to make this in a plot in R, and it was like the most unreadable thing ever. So, people up here are positive amounts away from their exam score. Yes, can we all agree they're above the average on the exam? Here, they're below the average. So that makes the exam score positive over here and negative over here. For anxiety, people over here are below average. People over here are above average. So what we have is when exams are positive, anxiety is negative, right, because they're below average. And when exams are negative, anxiety is positive. So we basically have this combination, which is why it's a negative correlation. Because when one of them's positive, the other one's negative, and the reverse. So if one variable scores are above the mean when the other variable scores are below the mean, it's a negative correlation. If they're both above the mean at the same time, or both below the mean at the same time, it's positive correlation, because they match. So all correlation tells you is if it's a mismatch, it's a negative correlation, or a match. They're both going up, they're both going down. And that's technically covariance. So covariance is a variation on a theme from variance. So variance tells me how much scores deviate from their own mean, which is sum of squares. So everything we've been doing has been variance. Covariance is when you have two of them at the same time. So let me show you the formulas. Hopefully that'll make more sense. So here's the formula for variance. It's x minus its own mean, so me minus the grand mean, me minus the level mean, all that stuff, squared. Remember, we have to square it because 0, otherwise they add up to 0. It's not a useful number. So the formula, if you write it all out, is x minus the mean twice. And that's with one variable. Watch what happens with covariance. Now there's two. So it's x minus the mean times y minus its mean. So all we've done is switch out double x's for one variable to x and y for two variables. So covariance is the difference from the mean of both x and y at the same time. And you'll get a negative covariance if one's positive and one's negative, because when you multiply one positive and one negative, you get a negative. You'll get a positive covariance when they're both negative or both positive. So technically we're going to calculate covariance first. However, covariance is the same problem as regular variance. It is in its own, it's not squared anymore, but it's multiplied scale. So if x and y are both 100 points, covariance can get very large very fast. And if I told you the covariance was 4,025, you'd be like, well, it's positive. That's all I got. So the magnitude doesn't make sense. It's not interpretable. So normally the solution to that is to take the square root, right? And that takes it back to the scale of the variable. You can't quite do that here because it's not actually squared. So what we're going to do is standardize it. I'll show you that here in a second. So here's an example from the book. It's got advertisements watched and the number of things that you bought from it. Bought is British, so it's adverts and packets. And this is what I was trying to draw on the board. So for all of the advertisements, they are negative for the first three people, a positive for the second people. And these are negative and positive, so the two negatives go together, the two positives go together, so it's a positive correlation. Which math. Try to graph here. So if you did the correlation for this example, you would get a very high positive correlation because they're both below the mean at the same time and both above the mean at the same time. And if you math that out, the two negatives cancel each other out because a negative times a negative is positive. If I told you covariance is 4.25, you'd just kind of be like, Shrug. So, what do? We standardize it, which is the answer to everything. Like if you aren't sure, it's z-scores. That works in my undergrad class. I don't know if it actually works here, but close. Okay. So, divide by the standard deviations of both variables. Okay, so take that covariance and standardize it. The standardized version of covariance is what you're familiar with, Pearson's correlation coefficient. Okay, so Pearson's R. And it is relatively unaffected. Unaffected. Typo. So covariance is affected by the unit of measurement. Larger measurement scales get larger covariances. Correlation coefficient is actually totally unaffected by the measurement scale because it's standardized. So that's the math. That's kind of gross, but you divide by the standard deviation of x and the standard deviation of y together because I got two variables, and that is actually z-scores. So it's the z-scores multiplied by each other. So it is standardized. The cool thing about it being, look, math. All right. The cool thing about it being standardized is that I don't need an error term anymore. The error term is dividing by the standard deviation. So I don't have to tell you the error anymore. It's built into R. Now, it would be better if we told people what the confidence intervals were, because that'll give me a good idea of how believable R is, right? It'll give me a range around R. But instead of having two numbers, now we can just have one. Okay. So we can talk about model fit based on the strength of R. Okay. Does that make sense to people? Bigger R's, more believable. Not more believable, better. Little R's, worse. And we'll look at the confidence intervals to talk about believability. The cool thing about R is that not only is it the model and the error, it's also an effect size. So it's got lots of stuff built into one. So it varies between -1 and +1, where 0 is bad. Think about z-scores for a second. Z-scores, the mean is 0. And so if there's no correlation, you're going to get a 0, because the positives and the negatives will all multiply out to 0. +1 means a perfect positive relationship. -1 means perfect negative. Something I don't feel like I should have to tell you guys, but my freshmen can't get this right, is like -1 isn't bad, right? -1 is just negative. So in terms of strength, think about it as absolute value. Okay? So a -0.9 is better than a 0.5. There's something about negative numbers that people are just like, ooh, bad. I'm like, no, stop. Okay. Closer to 1, the better. It's also an effect size. So these are Cohen's measures for R. And this is why I said R squared is so confusing to me, because we've got R, it's 0.1, 0.3, 0.5. Everybody agrees on this. But then on R squared, we're like, what did I tell you guys that we're using? 0.01, 0.06, 0.14? Yeah, something like that. That was one of the options. That does not match. R and R squared. If I square 0.3, I don't get 0.06. So I've always gone with 0.01, 0.09, 0.25, because then R to R squared, square them. But that's not what people want, so. But these agree. Yes, everybody likes these. So 1, 3, and 5. So 0.1 is a small correlation, 0.3 is medium, 0.5 is large. Good luck working with people. Correlations will be small. There was one time I had a project with my advisor where he got like a 0.98. I was like, you've screwed something up. He's like, I know, but I can't figure out where. And we didn't. I don't know how it happened, but I don't even remember what study it was anymore, but it was like almost perfect. And people thought we had screwed it up too. We had to convince them like, no, we promise.
You guys were just that good.
I think it was the data we were working with was magic. Never happened again. Sometimes R squared is called the coefficient of determination. That's like super stat nerd people. You can just call it R squared if you want. So by squaring R, you get proportion of variance in one variable shared by the other variable. Okay, so what does that mean? And we're going to do this a lot next week. So if I have exam scores and anxiety scores, this is R squared. So it's how much of their variance, their covariance, right, all they're going up together or going down together, overlaps. So when we get into regression and we're trying to predict variables, we're seeing how much we can predict with the x variables. So I think that's where the term comes, coefficient of determination. How much of this variable can I determine? Okay, so it's proportion of shared variance. So effect size wise, you can't think about this one like we do Cohen's d, which is how different are they. So Cohen's d of 2, you're like, wow, they're really different. You get an R of 2, you've done something wrong, because it only goes from 1 to 1. But 0.3 is now they overlap by 9%, or 0.3 correlation. And so I think that's why people like to talk about R squared, because it's in a scale that makes more sense. So if I tell you the correlation's 0.5, you're like, okay, cool. If I tell you it's 25% of the variance, like there's just a number we understand better. So people will square them to talk about variance overlap, which is the same idea as eta. Okay. So eta is how much of the IV accounts for the differences in means, but now that we have two continuous variables, it's how much of the IV accounts for the dp. Lots of this hand motion today. This is not in the book, and this confuses the heck out of people. So this is for this week and next week. Big R, capital R, is the correlation coefficient for 3 or more variables. That's used in multiple regression. So when I have the relationship between lots of x's and one y. Little r is 2 variables, 1x, 1y. Little r squared is the effect size for 2 variables. Big R squared is for 3 or more variables. So the distinction between little r and big R is the number of x's. People don't understand this. And everybody just uses big R squared for everything, even though it's not appropriate. So if you see on the output, the distinction is the number of x variables. Generally, people talk about little r squared when they're doing correlations, big R squared when they're doing regression. So let's do an example. We already got this data set loaded, hopefully. So we've got time spent revising their exam performance, anxiety, and gender. If we were to screen this for correlation, yes, you still have to screen the data. I told you would get tired of it, and it would be easy. Right, so accuracy, missing, if you're doing correlations, excluding pairwise. If you've got multiple correlations you're calculating, don't delete a whole line, just exclude them pairwise. Outliers are super important when we get to regression because they can have a large effect on slopes. So checking them for correlation, normal, linear is probably the most important, or you should not be doing Pearson. Homogeneity and homoscedasticity. So all the same ones we've been doing with a special emphasis on linearity. You'll notice that multicollinearity is not on there, additivity, because that's the point of correlation. So when we get to regression, we have to add it back, though. And we'll talk about that next week. So how do I do this? You've actually already been doing it as part of data screening. I'm just going to add more to it now. So one function is core, x comma y. But you'll notice that core does not give you p-values. So everything we've done so far is just looking at the magnitude of the correlation. Is it over 0.9 or is it not? If it's over 0.9, I have to worry. If it's not, whatever. We haven't really gotten into is it significant? Okay. So, go back to my notes here. I worked out that covariance example, but we already kind of went over it. So we can skip to correlations, or I can show you the pretty graph of adverts versus packets with the line on it. Ooh. So that's how I made the picture that's in the notes. So you'll need the HMISC package. You already have it on your computer, I promise. It is one of the ones that does error bars for ggplot. So you will want to load that one up. It is not automatically on, so turn that one on. So what we're going to do is use the normal correlation function and then talk about these other two, rcore and core.test. So what about p-values? So there are way too many of these. These are like the simplest three functions that will calculate Pearson's, Spearman's, and Kendall's, and we'll get into what are those other two here in a little minute. And then core will calculate multiple ones at once, meaning it'll calculate exam to anxiety, exam to revision, anxiety to revision. It'll do the table for you. So that's why we've been using that function for data screening. Our core will do Pearson and Spearman's, but not Kendall's. Don't know why. It'll give you the p-value and do multiple correlations at once. Core.test will calculate Pearson, Spearman, and Kendall, p-values, and the confidence interval. Yes. But you have to do them one at a time. Why can't we have one that does all of this? That would be great. But alas. So we will use all three depending on what type of question you're being asked. Okay. So let's talk about how they work. Okay. So core will give me everything. So I have exam data. You'll notice in the code I have to drop a couple columns. Remember that you can't use factored variables. Doesn't like that. So I dropped 2 columns that I wasn't caring about. We've got my use pairwise complete of, so that'll drop NA values pairwise. We've used that before too. And then this new thing, method equals Pearson. That's actually assumed, it's the default. But when we get into Spearman and Kendall, that's what you'll change. So you don't have to have it for Pearson, but when you do the other ones, you do. So that will give you the correlation table. So that's line 67-ish. And since we haven't looked at these, really, we've been doing the symbols table. What happens is you get the ones here, that's the diagonal, and that's it's correlated with itself. Okay, so if there aren't ones there, something's bad. Okay. And then it's each one correlated together. So exam and revision are 0.4. You get the same thing here. So the top half and the bottom half are the same until we get into something else. Anxiety and revision is negative 0.71. So the more anxious I am, the less I revise, or the reverse. The more I revise, the less anxious I am. And anxiety and exam, this is 0.44, so it's a negative correlation. The more anxious I am, the worse I do. So those are just the correlations, though. How do I know if that's significant? And that's where our core comes in. The sneaky part about our core is it requires the format of the data to be a matrix. Why can't we all agree to play along? Right? So as.matrix just puts it in the right format. Okay. So I'm going to make my data a matrix, and then its type equals Pearson, because clearly the same two people did not make core where it's method and R core where it's type. Okay. So it's type equals Pearson rather than method equals Pearson. Okay. It does automatically do pairwise deletion, so there's no use function or NA function. Everything has to be numeric. So drop your categorical variables as well as matrix. And that is in the HMISC library. So that's 67. So you'll see I just dropped my two categorical columns, gender and code. Type equals Pearson as dot matrix. So you just gotta get the parentheses in the right place. That's the tricky part. And the nice thing about that, I don't love that it rounds to 2 decimals, but okay. So it'll give me the correlation table first. It tells me N, and then P down here. Never fails. Someone always calls me in this class. Okay. So this here is super helpful, right? 0. So I would assume this means that P is less than 0.01 since they're doing 2 decimals here, but you didn't do anything wrong if you got this table, basically is what I'm trying to say. So all of these look to be significant because the p-values are all very small. But if you don't trust this table, what you can do is core.test. So the problem with core.test is you have to do 1 column at a time, or 2 columns at a time. So you can't do all 3 correlations at once. So it's x comma y. It's single vectors or columns at a time. Method, we've gone back to method, it goes Pearson. So what I did was exam data, so I've got my $sign operator. You can also use the with function. So I got exam and anxiety. Now the thing I like about this one is that it gives me all of my significance testing. So it not only shows me P, it shows me the T value it calculated. So correlations are either calculated by either doing Z or T, depending on what formula we're using. It gives me my degrees of freedom, which you never see people report unless you end up with someone from one of those quant places going, we have to report degrees of freedom. I'm like, fine. It's N-2. I could math that myself. Thanks. And then here's P. So that's why it became up as 0, because it's to the -6. Okay. But then here's the best part. It gives me my confidence interval here. So how believable is this correlation? I've got -0.44, wherever it went, here. And so the range around that is from 0.27 to 0.58, which is pretty small. Yeah.
Do we want to remove scientific notation for this?
You can if you don't like scientific notation. I never remember to turn it on until I'm like, well, I can't remember E.01 math. You can turn it off if you don't like it. So how believable is this correlation? Well, that's a pretty small confidence interval. Okay, so it's like 0.1 down, up and down. Okay. The range of it is from a medium correlation to a large correlation. So I would say this is somewhere to medium to large. So I would tell you to use core.test if you're wanting confidence intervals. If you just want quick p-values, I would use R-core. If you're doing data screening, I'd stick with core, because you don't really need to know if it's significant or not. You're just trying to know if it's too big or too small. Okay, that. One more slide, and then we'll take a break. So everyone knows that correlation is not causation. If you don't know that, you've like missed every psych lecture ever. Right? It's Freud and that sentence. But then one of the bigger issues is the third variable problem, and we'll talk about partial correlations at the very end, so how can I deal with that? But the problem is that correlations often are affected by some other variable. So the example people always give is like ice cream sales and shark attacks are positively correlated. So as people eat more ice cream, they get attacked by sharks more, or vice versa. And really the issue is that as it's warm outside, people go outdoors to the beach and they buy more ice cream. So that's a third variable problem. So it affects both variables at once. So when we do multiple regression, we'll talk about how do I control for third variables, or it could be mediator or moderator. So using those variables as part of your analysis. Okay. So we can't determine cause because of that third variable issue, and you can't determine which way cause goes. So correlation is a stat. Okay, there's correlational designs, but correlation itself is a statistic, and statistics don't care about your cause. Okay, you just got to think about it that way. They're just numbers. So cause is determined by experimental design, not the statistic picked. So even with ANOVA, it could not be causal. People talk about it in a causal way, but it's like cause is determined by design, manipulating the variables, not the statistic itself. Okay. And so that's when you interpret in correlation coefficients, you have to be careful. Like as exam scores go up, anxiety goes down. But it also could be as anxiety goes up, exams goes down. It could be either direction. And it could be a third variable, totally unrelated. So as your comfort with computers in this version of this class goes up, you're less anxious about it, so you can score better. That is a good place to break, because then we'll do non-parametrics.